Let's all picture the ocean on a moonlit night. No ships nearby, no cities glowing on the horizon, just water, endless water. The waves rise and fall under a sky filled with stars. The air smells like salt and wind. Somewhere in the darkness, something splashes, then disappears again beneath the surface. Now imagine standing on the wooden deck of a ship. Lanterns sway gently in the breeze. Ropes creak. The hull groans softly as the vessel rocks back and forth. Sailors move quietly across the deck while a group of scientists lean over the railing, staring down into the black water. They are about to lower a rope into the sea. Not just a short rope, not even a long one. Miles of rope. They want to know something that, at this moment in history, nobody on Earth can answer. How deep is the ocean? It might take hours for the weighted line to reach the bottom. Maybe it will, maybe it will not. No one really knows. Because in the late 1800s, the deep ocean was still a mystery. Some people believed nothing could live in the darkness far below. Others thought the seafloor might be covered in strange mud or towering underwater mountains. There were maps of continents and rivers and deserts, but almost nothing about what lay beneath the waves. The ocean was the largest unexplored place on our planet, and one ship was about to change that forever. A ship filled with curious minds, delicate scientific instruments, and an enormous question about the hidden world below. This week, we are stepping aboard that ship. This is the story of the voyage that revealed the deep ocean to humanity. Welcome back to Saltwater Stories, where this week we're rediscovering the expedition of the HMS Challenger.
It really is such a haunting visual to start with, just casting off into that endless blue, leaving everything known behind.
Yeah, exactly. And I am just so incredibly excited to unpack this whole ocean adventure with you today. And for you listening right now, because, well, these brilliant minds were doing super serious science, right?
Oh, absolutely. Groundbreaking science.
Right. But we also have to remember they were, just regular humans living on a rockin', rolling wooden boat for 4 whole years.
That is a very long time to be stuck at sea.
It totally is. So before we get into the heavy scientific discoveries, I kind of want to share a super quick, funny snapshot of what life was actually like out there.
I love these behind-the-scenes details. Please do.
Okay, so picture this. You are spending 4 Christmases in a row out at sea. You're thousands of miles away from your home, your family, your cozy bed.
You're probably freezing cold, too.
Oh, freezing, bouncing up and down on these massive ocean swells. So for the crew, the absolute pinnacle, like the biggest highlight of the entire year was the Christmas dinner.
Naturally. A little taste of home.
Exactly. The ship's cooks had actually meticulously hidden away these special roast geese and whole turkeys just to give the officers a proper holiday feast.
That takes some serious planning with no refrigeration.
It really does. But here is the crazy part. One year, a sneaky, totally unidentified thief kept stealing the birds right before dinner.
Wait, really? On a closed ship, there is literally nowhere to run. That is a bold crime.
I know. The officers were completely baffled and, well, probably furious. I mean, they searched everywhere. The galley, the sleeping quarters, the storage holds, nothing.
So where did the birds go?
Well, the mystery was partially solved when some sailors happened to look up. And I mean, way, way up.
Oh, no.
Yeah. They found the picked-over bones and chewed-up fragments of the holiday birds hidden at the very top of the ship's towering rigging.
The rigging. As in the massive network of ropes and sails.
Yes, someone, or, maybe some incredibly clever animal, had swiped the holiday dinner and climbed hundreds of feet into the freezing air just to eat it in absolute secret.
That is incredible. Did they ever figure out who did it?
Nope. The actual thief was never caught. But it's just this brilliant, hilarious glimpse into the wild, totally unpredictable daily life of these seafaring scientists. It wasn't just quiet reading in a lab. It was a rough, dramatic adventure every single day.
That really paints the perfect picture for our destination today, because for this exploration, we are traveling back to the 1870s. And our mission today is to help you comprehend exactly how a wooden warship, a vessel literally built to fire heavy cannons, was completely transformed to launch the entire modern science of oceanography.
It's just a huge transformation.
It truly is. And over the course of this journey, we're going to uncover how this remarkable crew discovered invisible underwater mountain ranges, pulled up actual literal space dust from the ocean mud.
Space dust. I still can't get over that part.
And captured bizarre, mysterious creatures that grow in the dark.
So cool.
Yeah.
But to really appreciate the massive scale of what the HMS Challenger accomplished, we first kind of need to erase everything we currently know about the ocean.
That's a great point. We have to set the stage.
Right. We have to look at what human beings actually believed before the year 1872. And the truth is, what they knew about the deep ocean was, well, effectively zero.
Zero is accurate. If you were a sailor, a navigator, or even a map maker before the late 19th century. Your knowledge was strictly horizontal.
Horizontal meaning just the surface.
Exactly. You understood the surface of the water with incredible precision.
Hmm.
You knew how to read the stars to find your location. You understood the powerful surface currents, and you knew how to harness the wind.
But looking down was a different story.
Completely. If you look straight down over the railing of your ship,
Yeah.
that vertical drop was just a terrifying, absolute blank void.
And human nature has a very specific reaction to a dark, blank void that we can't see into. We fill it with our imaginations.
We certainly do.
Like if you look at old maritime maps from the centuries leading up to this era, you will not see careful depth charts. In the empty, unexplored patches of ocean, mapmakers literally drew terrifying monsters.
Because an empty map is unsettling.
Totally unsettling. So you'd see these elaborate illustrations of massive krakens with tentacles thick as tree trunks wrapping around entire ships and pulling them under. You'd see giant sea serpents with jagged teeth and glowing eyes.
And because no one had ever gone down to the bottom to check, those myths went completely unchecked. The deep ocean was widely considered this realm of nightmares.
But the wild thing to me is that it wasn't just superstitious sailors. Even the most highly educated scientists of that era were making these massive, sweeping assumptions based on almost no evidence.
That's true. By the mid-1800s, the scientific method was replacing mythology, but a major misconception took hold. The leading scientific minds firmly believed that the deep sea was a completely dead, frozen wasteland.
And this brings us to a really crucial concept in the history of marine biology, the azoic hypothesis.
Yes, the azoic hypothesis. To understand this, we have to look at a prominent British naturalist named Edward Forbes. The year is 1841.
Okay, 1841, where is he?
He is sailing around the Aegean Sea, which is a part of the Mediterranean, and he's doing some early marine biology. He's dropping a net attached to a rope to scrape the shallow seafloor and catch marine animals to study.
Sounds like standard science.
It was. And as he works, he notices a very consistent pattern. The deeper he drops his net, the fewer plants and animals he brings back up to the surface.
Okay, so the deeper he goes, the less life he finds. That makes sense on the surface.
Forbes was a meticulous observer, and his data for that specific location was correct. However, his mistake was extrapolating that localized pattern to cover the entire global ocean.
He assumed the whole world worked like that one spot in the Mediterranean.
Exactly. And to understand his logic, it really helps to use an analogy that makes perfect sense on land. For those of you listening, consider the experience of climbing Mount Everest.
Oh, that's a great way to picture it.
When you begin your journey at the base of a massive mountain, the environment is teeming with life. There are lush forests, countless insects, birds, and mammals.
Because the conditions are easy to survive in.
Precisely. But as you hike higher and higher in elevation, the environment becomes increasingly hostile. The air gets incredibly thin, making it hard to breathe. The temperature drops well below freezing. The fierce winds tear away the soil.
Right, and by the time you reach the very peak of Mount Everest, you're standing in a frozen, barren zone where almost no living thing can permanently survive.
So Forbes took that perfectly logical idea of climbing a mountain, and he essentially flipped it upside down for the ocean.
He reasoned that if going up into the extreme cold and thin air kills off life, then going down into the extreme cold, absolute pitch-black darkness and crushing water pressure must do the exact same thing.
Exactly. He ran some calculations and boldly declared that past a depth of about 1,800 feet, the ocean would become a completely frozen, high-pressure desert.
And he officially named this the azoic zone. And for you listening, if you break down that word, azoic literally translates from Greek to mean without life.
And because Forbes was so respected for decades, the entire global scientific community accepted the azoic hypothesis as an undeniable fact. They just pictured the bottom of the ocean as a quiet, completely empty expanse of thick mud where absolutely nothing lived.
But the beauty of science is that it is always willing to test its own rules, right? Even if it happens by total accident.
Often by total accident.
So let's fast forward from the 1840s to the 1860s. The world is changing rapidly. The telegraph has been invented.
Which was a massive technological leap. It allowed people to send instant electrical messages over long distances.
Right. And to connect different countries, engineers started laying these massive, heavy telegraph cables all the way across the bottom of the Mediterranean Sea. But occasionally, these heavy metal cables would snap or break in the deep water.
And to fix them, repair ships had to drop grappling hooks, snag the broken cables, and haul them all the way up from a mile deep.
which is an insane amount of heavy lifting. But this routine maintenance task provided the undeniable physical evidence needed to shatter the azoic hypothesis.
It absolutely did. When these engineers hauled the broken telegraph cables up to the sunlit surface from over a mile down, they noticed something extraordinary.
The cables were not clean. They were completely encrusted and covered in thriving marine life. There were deep-sea corals, various clams, and intricate tube worms securely attached to the metal, completely happy and alive.
Just put yourself in the shoes of that telegraph engineer.
I can't even imagine. You expect to pull up a boring, muddy wire, and instead you are staring at a wriggling, colorful, living garden pulled straight out of a place where every textbook on Earth said life was impossible.
It was a massive wake-up call for the scientific community. This very simple cause and effect observation caught the attention of two highly influential scientists, Charles Wyville Thomson and William Carpenter.
And they realized immediately that Forbes was wrong.
They did. Life clearly existed in the deep. But a few random observations from a broken telegraph cable were not enough to understand the mechanics of the entire global ocean.
Right, pulling up one wire doesn't tell you how the whole ocean works.
Exactly. They argued passionately that humanity needed to stop guessing and start measuring. They approached the British government and demanded funding for a massive, unprecedented, worldwide scientific expedition.
The goal was to systematically study the deep sea across every major ocean on the planet. I mean, they were basically asking for the 19th century equivalent of a massive space program, but aimed downward into the crushing depths.
The cost and risk were astronomical. But, incredibly, the government agreed.
Which is mind-blowing. But a mission of this magnitude could not be accomplished on a standard fishing boat. They needed a massive, powerful, incredibly sturdy ship to handle the extreme weather of the open oceans and carry all the heavy scientific gear.
They needed a beast of a ship. Enter the HMS Challenger.
Tell us about this ship, because it wasn't built for science originally, was it?
Not at all. The HMS Challenger was a magnificent vessel, originally constructed in 1858. It was a Royal Navy wooden corvette.
A corvette. What does that mean in the 1800s?
In the context of the Victorian Navy, a corvette was a smaller, highly maneuverable class of warship. It was 226 feet long, which provided ample deck space.
That's a good chunk of space.
Crucially, it was a hybrid vessel. It featured the traditional towering wooden masts and massive sweeping canvas sails of a classic sailing ship. But hidden deep inside its thick wooden hull was a massive coal-fired 1,200 horsepower steam engine.
Having both wind power and steam power is going to become the secret weapon of this entire expedition. But they had a major problem right at the start.
They did.
You cannot exactly conduct delicate, precise scientific experiments on a ship that is currently packed with heavy iron cannons and highly explosive gunpowder.
No, that would be incredibly dangerous.
So in June 1872, they sailed the Challenger into the Sheerness dockyard in England for what was basically the ultimate extreme makeover. They completely gutted the interior of this fierce military warship and transformed it into the world's very first floating oceanographic laboratory.
The physical transformation required brilliant Victorian engineering. The first order of business was disarmament. They removed 15 of the ship's 17 heavy cannons.
So they kept 2, just in case.
Yes, standard precaution. But by clearing out those massive guns and the accompanying ammunition stores, they freed up a tremendous amount of space on the main deck, which was then entirely redesigned to accommodate the scientific work.
Let's take a mental tour of this floating laboratory with you right now, because the problem-solving skills of these engineers were just brilliant.
It was a logistical marvel.
Imagine trying to do highly delicate chemistry, using fragile glass tubes and boiling liquids, while you are standing on a floor that is constantly tilting back and forth. That is what being on a ship in the open ocean is like. Every time a wave hits, the whole room moves.
It's an incredibly unstable environment.
So on the port side, which is the left side of the ship as you face the front, they built the natural history workroom. This room was essentially a giant library of biology.
Packed with very fragile items.
Exactly. Thousands of fragile glass specimen jars, sharp dissecting tools, and massive barrels filled with gallons of a preserving alcohol they called spirits of wine.
Which you absolutely do not want spilling everywhere during a storm.
No. So to keep all this fragile glass from flying across the room and smashing against the wall, they had to design highly specialized wooden racks with deep grooves to lock everything in place. They even had to take their heavy, expensive brass microscopes and physically clamp them down tightly to the thick wooden tables.
Securing the biology equipment was one challenge, but the starboard side, the right side of the ship, housed the chemical laboratory. This presented a far more dangerous problem.
Fire on a wooden boat.
Exactly. To conduct chemical analyses of seawater, scientists frequently need to heat or boil the samples using open flames. Boiling dangerous hot chemicals on a wooden ship that is violently pitching and rolling in the waves is an absolute recipe for a catastrophic fire.
So how did they fix it?
To solve this, the engineers installed swinging tables, known technically as gimbal platforms.
I love this part. This might be one of my favorite engineering tricks on the whole ship. For you listening, if you've ever seen those fancy electronic camera stabilizers, the ones where a person can run down the stairs but the camera stays perfectly smooth and level, that is the exact same concept as a gimbal.
A simple but brilliant mechanical solution.
The engineers built these heavy wooden tables and hung them from the ceiling using special pivoting metal hinges. Because the table was hanging freely, gravity always pulled it straight down.
So regardless of what the ship was doing, the table reacted to gravity.
Right. So if a massive wave hit the ship and the floor leaned hard to the left, the table would smoothly swing on its hinges and stay perfectly, completely horizontal. A scientist could have a beaker of liquid boiling over a flame right there on the table, and it wouldn't spill a single drop, even while the scientists themselves were struggling to stand up straight on the slanted floor.
It was an elegant solution to a terrifying problem, a true triumph of practical engineering. However, for all the complex microscopes and gimbal tables, the single most important piece of equipment on the entire ship was remarkably simple.
And it took up a ton of space on the deck.
It was spooled up in massive coils on the open deck. Rope. They loaded exactly 181 miles of thick, highly durable Italian hemp rope onto the ship.
We really need to pause and visualize the sheer scale of that. 181 miles of thick rope.
It's difficult to even picture.
Let's put it this way. If you took that rope, tied one end to a post in Philadelphia, and stretched it out in a perfectly straight line, it would reach all the way to Washington, D.C.
That really puts it into perspective.
And they had every single inch of it bundled up tightly on a wooden ship, specifically designed to be lowered hand over hand down into the dark water.
With the ship fully outfitted, customized, and loaded with all that rope, we must turn our attention to the individuals who would call this floating laboratory home for the next 4 years.
Because it wasn't just scientists.
No, a scientific endeavor of this magnitude requires a highly dedicated crew, and the Challenger carried a truly fascinating mix of people.
There were about 243 people on board when they set sail, and you have to picture two totally different worlds colliding in this small space.
A literal culture clash on the high seas.
Definitely. On one side, you have the Royal Navy sailors. These are rough and tumble, highly disciplined, weather-beaten men who are used to climbing hundreds of feet up into the rigging during raging storms, scrubbing the wooden decks and hauling heavy lines.
And on the other side,
You have a small six-person team of highly educated, well-spoken civilian scientists from the top universities. The sailors affectionately nicknamed this tiny group of academics the scientifics.
it was a remarkable mix. The military men valued order, speed, and strict obedience, while the academics valued slow, methodical observation and questioning. Yet, to survive the extreme conditions of the open ocean and succeed in their mission, they had to learn to work in perfect harmony.
And who was leading this team of scientifics?
Leading the civilian team was Charles Wyville Thomson. As the chief scientist, he was a serious, visionary figure from Scotland. He carried an immense psychological burden. He had convinced the government to spend a fortune on this expedition, and the pressure to produce groundbreaking results was squarely on his shoulders.
Talk about pressure. And he had a younger scientist with him, right? John Murray?
Yes, John Murray was incredibly energetic,
Yeah.
a laser-focused researcher born in Canada. When the voyage started, his primary job was simply to study the mud they brought up from the bottom.
Just staring at mud.
But he became so utterly obsessed and dedicated to analyzing every single grain of sand and crushed shell that history now officially recognizes him as the father of modern oceanography.
That's such an amazing title to earn. But we also have to talk about the artist, John James Wilde, because his job sounds so stressful to me.
His role was absolutely vital to the scientific record.
It's such a cool job because we have to remember the context of the 1870s. You listening right now probably know how easy it is to capture an image. We all have devices in our pockets that can snap 1,000 high-definition full-color photos in a matter of seconds.
But the Challenger crew did not have digital cameras.
Right. Photography existed, but it was incredibly slow, required heavy glass plates and messy chemicals, and most importantly, it could only capture images in black and white.
So documenting the color of these creatures fell entirely to Wild.
So, John James Wilde had arguably one of the most fast-paced jobs on the entire ship. Imagine the sailors hauling a net up from the freezing, pitch-black depths. Inside is a bizarre, alien-looking fish glowing in vibrant neon blues, bright reds, and brilliant yellows.
A spectacular sight.
But the moment that deep-sea creature hits the warm air and the bright sunlight on the deck, its vibrant colors instantly begin to fade away.
The colors degrade so rapidly.
Wilde had to stand right there, gripping his paints and pencils, racing against the clock. He had to furiously paint the creature the very second it came out of the water, capturing its exact true colors before they turned gray and disappeared forever.
It was a monumental task of rapid biological documentation. He preserved the visual truth of these creatures for the scientists back on land. But, to truly understand what the daily reality was like for the people on board, we rely heavily on another crew member.
Oh, you mean the letters?
Yes, the personal letters written by a 19-year-old steward's assistant named Joseph Matkin. While the senior scientists were busy writing formal, dry, highly technical reports about water temperature and barometric pressure, young Matkin was writing long, highly detailed, juicy letters home to his family.
Joseph Matkin is the absolute best source we have. He is the one who gives us all the behind-the-scenes gossip and the gritty details of what it was really like.
He didn't hold back.
Thanks to his letters, we know that life on the Challenger was absolutely not luxurious. For one thing, the food was notoriously terrible.
Food spoilage was a constant battle.
Remember, the ship had no refrigerators, no freezers, and no microwaves. So for months at a time, when they were far away from any port, the crew survived on a diet of hardtack.
Which is essentially a flour and water biscuit baked until all the moisture is gone.
Yeah, these incredibly dense, rock-hard flour biscuits that you often had to smash with a literal tool just to bite into without breaking a tooth. And they ate that with heavily salted dried beef or pork that was preserved in barrels. Eating tough, salty jerky and rock-hard crackers every single day for years takes a serious toll on your morale.
The physical toll of the diet and the constant labor was immense. But the psychological toll of extreme isolation was perhaps an even greater challenge. Staring at the blank, unchanging horizon of the open ocean for months on end can lead to profound boredom and depression.
So how did they stay sane?
They had to become highly creative in inventing their own entertainment and building a sense of community.
They actually planned ahead for this, which I find so endearing. Before they left port, some of the crew pooled their money and bought a bunch of brass musical instruments. They started their very own ship's brass band.
It's a wonderful image.
On calm, clear nights when the ocean was flat and the stars were out, the band would set up on the deck and play lively music. These rugged, tough naval sailors would actually dance with each other under the stars just to blow off steam.
They also sought out companionship by adopting a pet, didn't they?
Yes. When the ship was sailing near the freezing, desolate islands of the Southern Ocean, the crew adopted a dog. They named him Sam.
A ship's dog.
There are these wonderful historical photographs of the serious naval officers standing on the wooden deck, bundled up in heavy winter coats, with little Sam the dog happily sitting right at their feet, acting as a vital morale booster for the entire crew.
Those genuine moments of humanity are vital for understanding the full scope of the story. These were real people enduring extreme conditions. And speaking of extreme conditions, the Challenger expedition achieved a remarkable geographical milestone in the Southern Ocean.
Oh, right, the icebergs.
Yes. They became the first steam-powered ship in recorded history to cross the Antarctic Circle. They sailed directly into violent, blinding snow blizzards, constantly scanning the horizon to dodge massive, lethal icebergs that could have easily crushed their wooden hull.
That sounds absolutely terrifying.
It was. But amidst that terror, the ship's official photographer, a man named Frederick Hodgson, actually braved those freezing below-zero temperatures. He carried his heavy, delicate camera equipment and volatile glass plates out onto a rocking, icy deck.
And he actually managed to take photos.
He managed to capture some of the very first photographs of massive, cathedral-like icebergs ever seen by the general public.
Just picturing that scene in your mind, a 226-foot wooden ship completely surrounded by towering, silent mountains of glowing blue ice is absolutely incredible. But dodging icebergs and surviving the cold was really only a small part of their job, wasn't it?
That's right. Their primary mission was to actually conduct science. And doing highly precise science without modern electricity, relying entirely on Victorian mechanical technology and raw human muscle, was an utterly exhausting process.
So how did they actually do it? Because taking a measurement in a moving ocean seems impossible.
The logistical challenges were staggering. Let's consider the mechanics of taking a simple depth measurement. The foremost obstacle was a maneuver known in naval terms as station keeping.
Station keeping.
Yes. If your objective is to drop a weighted rope in a perfectly straight line down to the bottom of the ocean to accurately measure the depth, your ship cannot be drifting.
Let's think about the physics of that for a second. If the wind is blowing your ship forward across the surface, your rope isn't going to fall straight down.
It would drag behind.
It's going to trail out behind the ship at a long angle. If you measure an angled rope, you might think the ocean is 5 miles deep, when really it's only 2 miles deep and your rope is just dragging sideways through the water. Your measurement would be completely scientifically useless.
Therefore, whenever the navigators determined they had reached a specific coordinate on their map, a location they referred to as a station, the captain would order all the massive canvas sails to be furled and tied down.
So they stop sailing.
They stop sailing and they ignite the furnaces to fire up that powerful 1,200 horsepower steam engine we discussed earlier. The ship's helmsman would then face a grueling test of skill.
Because he has to hold the ship still.
Exactly. For up to 12 hours straight, the helmsman had to use the power of the steam engine to perfectly counteract the force of the wind and the pull of the ocean currents, actively driving the massive wooden ship to keep it perfectly still in the middle of the open ocean.
Holding a ship steady against the chaotic forces of the ocean for 12 hours requires a level of driving skill that is just wild to think about. And while the helmsman is fighting the ocean up top, the rest of the crew gets to work actually measuring the depth.
Which they called sounding.
Right, sounding. Now you might be thinking, why is this hard? Just tie a heavy rock to a string, drop it over the side, and wait for it to hit the bottom.
If only it were that simple.
But when you are dealing with miles of ocean water, it is far more complicated. Ocean water is thick, and there are powerful underwater rivers and currents pushing things around in the dark. If you just drop a rock on a rope, the friction of the miles of rope moving through the water will pull on the rock.
It could take days to sink.
And you would never actually feel the delicate moment when the rock finally touches the mud. So to solve this, they used an ingenious piece of mechanical technology called the Bailey sounding machine.
The Bailey machine was a masterpiece of mechanical problem solving, designed specifically for the abyss. It consisted of a central, hollow metal tube. Surrounding this central tube were several massive, heavy iron weights.
So it's super heavy.
Very heavy. The crew would securely tie this heavy iron contraption to their 181 miles of hemp rope and lower it over the side of the ship. The sheer massive weight of the iron would forcefully pull the rope down rapidly, cutting straight through the water column and the deep ocean currents.
But the absolute genius of the machine is how it solved the communication problem. Imagine you are flying in an airplane thousands of feet up above the clouds. You lower a long rope down to the ground.
A great analogy.
How on earth can you possibly feel the exact fraction of a second when a rock tied to the end of that rope gently touches the grass below? You can't. The rope itself is too heavy, you wouldn't feel the tiny bump.
The feedback gets lost.
So the Bailey machine was designed to tell the sailors exactly when it hit. When that central hollow tube finally smashed into the thick mud at the bottom of the ocean miles below, the physical impact triggered a clever mechanical switch.
And what did that switch to?
That switch immediately unlatched all of the heavy iron weights, allowing them to fall off the tube and sink into the mud, leaving them behind forever.
By shedding hundreds of pounds of heavy iron weights in an instant, the tension on the miles of rope stretching all the way up to the surface suddenly and dramatically changed.
The rope goes loose.
Precisely. The sailors holding the line of the deck would instantly feel the rope go slack in their hands. That sudden slack was the unmistakable signal that they had reached the bottom. At that moment, the crew would fire up a small steam-powered winch to begin the arduous process of hauling the miles of rope back up.
And it's easier to pull up now.
Yes, because the massive iron weights were left behind at the bottom of the sea. The steam engine only had to lift the weight of the rope and the much lighter hollow tube.
And the most brilliant part of the design. When that hollow tube smashed into the seafloor to trigger the switch, it drove itself deep into the dirt, capturing a perfect, undisturbed core sample of the deep ocean mud for the scientists to study on the deck.
It is such an elegant, brilliant mechanical system. Mud and depth in one swift action. But they weren't just interested in measuring the distance to the bottom and grabbing mud. They also needed to measure the properties of the water itself.
Like the temperature, which brings up another massive physics problem.
It does. How do you measure the temperature of the water 3 miles down? If you take a regular standard glass thermometer from a laboratory and send it down into the trench, the insane weight and pressure of all that water pushing from the outside will instantly crush the thin glass into fine powder.
So they had to build special ones.
They did. The engineers provided them with Miller-Casella thermometers. These specialized instruments were wrapped in incredibly thick, highly pressure-resistant outer glass shells, creating a protective bubble so the delicate measuring instruments inside wouldn't implode under the crushing weight of the ocean.
So smart. Measuring the temperature was critical, but the chemists, particularly John Young Buchanan, also needed to bring up actual, uncontaminated samples of the deep water to test its exact chemical composition.
And you can't just use a bucket for that.
Right. If you just lower an open bucket, the deep water will mix with all the layers of shallower water as you pull it back up, ruining the sample. To solve this, Buchanan utilized devices known as slip water bottles.
These devices were so clever. They were essentially long brass tubes with a hinged lid on the top and another lid on the bottom. The sailors would lower the brass tube down on the rope with both lids locked completely open.
This meant that as the tube sank deeper and deeper, the ocean water would just flow right through the open tube without being trapped.
Exactly. When the tube finally reached the exact depth the scientists wanted to measure, say exactly 2 miles down in the dark, a sailor standing on the sunlit deck would take a heavy metal ring, which they called a messenger weight, clip it directly around the rope, and simply drop it.
And it slides down the rope.
That heavy metal ring would zip all the way down the rope, slicing through the water for 2 miles, until it smashed hard into a release trigger on top of the brass tube. Snap. Both lids would slam completely shut at the exact same moment.
That is incredibly satisfying. It permanently trapped that specific deep-sea water inside the brass cylinder, so it wouldn't mix with any of the warmer, different water near the surface as the steam winch hauled it all the way back up.
This rigorous, highly mechanical approach to sampling, stopping the ship, holding station, dropping the Bailey machine, sending down the thermometers and the slip water bottles, was repeated hundreds of times across the globe.
And all that hard work paid off in a huge way, because by diligently plotting all these individual depth measurements on a map, the Challenger expedition began mapping the invisible world beneath the waves.
Before this voyage, the prevailing geographical assumption was that the deep ocean floor was essentially a flat, featureless plain, much like a flooded, muddy desert stretching out endlessly.
But the data they were bringing up proved that assumption was entirely wrong. Imagine the crew sailing straight down the exact middle of the massive Atlantic Ocean.
The very center of it.
Every few days, they stop the ship, they go through the whole exhausting Bailey-sounding routine, and they meticulously chart the depth. Over the course of several weeks, as they plot the numbers on their paper charts, they start to notice something bizarre.
The numbers started shrinking.
Yeah. The water right in the middle of the ocean is actually getting much shallower than the water closer to the edges of the continents.
Without ever being able to see it with their own eyes, simply by plotting numerical points on a graph, the Challenger crew had mapped the contours of a massive, continuous underwater mountain range. They had discovered what we now call the Mid-Atlantic Ridge.
A completely hidden mountain range.
It is a staggering geological feature. It is the longest mountain range on the entire planet, winding its way around the globe, completely hidden beneath the waves.
Discovering the largest mountain range on Earth completely blind is a historic achievement all on its own. But they were far from finished. Here is where the voyage enters into absolute legend.
March 23, 1875.
Yes. The date is March 23, 1875. The ship is sailing through the western Pacific Ocean. The captain orders the ship to halt. They drop the heavy Bailey-sounding machine over the edge. The rope starts unspooling from the deck. It goes down a mile.
And it kept going.
The sailors keep feeding the line. 2 miles down, then 3 miles down. The crew members are starting to stare at each other. 4 miles down, the rope just keeps going and going. Finally, the line goes slack. The weights have hit the bottom.
When the crew hauled the line back up and carefully calculated the distance markings on the rope, The final depth was an astonishing 4,475 fathoms.
Which means what to us today?
To convert that into terms we use today, that translates to nearly 5 miles straight down, or exactly 26,850 feet. The scientists on board were so profoundly shocked by this extreme measurement that they immediately assumed their equipment had snagged or malfunctioned.
They didn't believe it.
They actually ordered the crew to reset the heavy gear and spent hours taking a second, agonizingly slow measurement just to confirm the unbelievable numbers.
And the numbers were completely real. They had accidentally dropped their line into the deepest place on planet Earth. Today, we know this massive underwater canyon as the Mariana Trench.
And the specific deepest spot within it is still named the Challenger Deep, in honor of the ship and the crew who first found it.
To really put that insane, mind-boggling depth into perspective for you, if you took Mount Everest, the absolute tallest mountain on land, plucked it up, and dropped it straight down into the Challenger Deep, its snowy peak wouldn't even poke out of the water.
It would be completely submerged.
The top of Mount Everest would still be completely covered by more than a mile of dark ocean water.
It is a scale of geography that almost defies human comprehension. But mapping the physical mountains and trenches was only half of the expedition's mission. The true marvel, the discoveries that fundamentally shifted human understanding, was what they found actually living in those terrifying depths.
Which brings us to the great carnival of wonders, the biology of the abyss.
Remember Edward Forbes and the Zoic Zone? That deeply held belief that absolutely nothing could survive past 1,800 feet.
Oh yeah, that got destroyed.
Completely.
Yeah.
Every single time the Challenger crew hauled up their deep-sea dredging nets from the freezing bottom, they completely dismantled that theory. The nets came up filled with wriggling, thriving life. By the end of their 4-year journey, the expedition had discovered and cataloged roughly 4,700 brand new, never-before-seen species.
4,700 new species. That is wild.
The sheer volume of biodiversity was staggering, especially in an environment deemed uninhabitable. And because these animals lived in an ecosystem completely alien to anything found on the sunlit surface, they possessed morphological adaptations that made them look like absolute monsters to the Victorian scientists viewing them for the first time.
Oh, they totally look like aliens from another planet. Let me describe some of these amazing creatures for you so you can picture what the scientists saw. First, they pulled up a bizarre fish that the scientists simply called the faceless fish.
A very apt name.
Imagine a bulbous, fleshy, pale fish, but when you look at the front of its head where the face should be, there are no eyes, none at all, and its mouth is completely hidden underneath its body, designed to slurp up food from the mud like a vacuum cleaner.
Which makes perfect evolutionary sense.
Right, because it lives in absolute pitch-black darkness where sunlight never reaches. Growing and maintaining eyes would be a huge waste of bodily energy. So over millions of years, it just evolved to not have them at all.
A perfect example of evolutionary efficiency. And then there was a remarkably strange creature that was affectionately described much later as the gummy squirrel.
The gummy squirrel. Imagine you are looking at a bright yellow, squishy piece of gummy candy. Now imagine that yellow jelly-like candy is alive, about the size of a banana, and it is slowly crawling across the thick mud at the bottom of the ocean.
It sounds made up.
It does, but it's actually a highly adapted, bizarre type of deep-sea sea cucumber.
They also discovered incredibly intricate biological structures, such as the famous Venus flower basket.
This one is actually incredibly beautiful, but also a little sad. It looks like a delicate, curved, hollow tube made entirely out of intricately woven glass fibers. It's a type of deep-sea sponge that builds a skeleton out of silica.
And it has some permanent residence inside.
That's the craziest part. Almost always, you will find a tiny pair of shrimp living inside this delicate glass cage. The shrimp swim inside through the tiny holes when they are microscopic babies looking for a safe place to hide.
But then they grow.
Right. As they eat and grow, they become too big to fit back through the holes. So the two shrimp spend their entire adult lives permanently locked inside this beautiful glass tower at the bottom of the sea, completely protected from predators but never able to leave.
It is a profound example of symbiosis.
Yeah.
And we certainly cannot forget the more formidable, aggressive predators they encounter, such as the creature we now know as the cookie-cutter shark.
Oh, this little predator is straight out of a horror movie. It's a relatively small shark, shaped somewhat like a cigar, but it has this perfectly circular jaw filled with rows of incredibly sharp, jagged teeth.
And it has a very specific hunting strategy.
It doesn't hunt small fish. It swims up to much bigger fish, or even massive whales, lashes its circular mouth onto their side, and violently spins its entire body in a circle to take a perfect round ice cream scoop bite out of them. It just leaves a perfectly round crater behind and swims away. It's like a swimming ice cream scooper of doom.
While these animals may seem bizarre or frightening, what is truly fascinating here is analyzing their structure and function. How exactly do they survive in an environment that physics dictates should be entirely lethal?
Yeah, how do they not get crushed?
Let's consider the crushing pressure first. As we established, the pressure at the bottom of the trench is immense. To conceptualize it, imagine the full weight of an adult African elephant perfectly balanced on your thumb.
That would instantly shatter bone.
If a human being or even a normal surface fish with hard, rigid bones and air-filled swim bladders traveled down to that depth, the air spaces would instantly collapse, and the rigid bones would shatter under the extreme pressure.
So how do the deep-sea animals survive the equivalent of an elephant on their thumb? They completely adapt their bodies.
They do away with rigid structures.
The deep-sea fish have very few hard bones. Instead, their skeletons are flexible and their bodies are super soft, almost jelly-like. They don't have any pockets of gas or air inside them.
And water cannot be compressed.
Exactly. Because their bodies are mostly made of water, the insane pressure of the deep ocean just passes right through their tissues without crushing anything. They are basically built to be flexible, uncrushable water balloons.
Precisely. They rely on special molecules called piezolites to keep their cell membranes flexible under pressure. And then there is the challenge of the absolute darkness.
Which is total blackness.
Below a certain depth in the ocean, sunlight simply cannot penetrate the water.
Yeah.
The deep ocean is completely, eternally black. To navigate, communicate, and hunt in this dark void, many animals developed bioluminescence, a complex biochemical reaction that allows them to emit their own glowing light.
They make their own glowing light from within. The Challenger crew actually pulled up an animal called Umbellula thomsoni, which is related to corals and jellyfish, and it literally glowed with a bright, haunting light right there on the wooden deck of the ship.
Seeing that in the 1870s must have been astonishing.
In the deep ocean, animals use these glowing lights like high-tech biological flashlights. Some species dangle a glowing light in front of their mouths to attract curious, hungry prey right into their jaws, while others suddenly flash bright lights to blind and scare away bigger predators. It's an entire silent language of light communicating in the absolute darkness.
Yet, if we look beyond the spectacular glowing predators and the giant sponges, the most globally important organisms the Challenger discovered were not the giant fanged fish. They were microscopic.
The really tiny stuff.
By dragging very fine mesh nets at the surface and at depth, the scientists collected billions of tiny organisms known collectively as plankton, specifically focusing on groups called Radiolaria and Foraminifera.
These are tiny, single-celled creatures, but if you clamp them under a brass microscope, they don't look like simple blobs. They build intricate, beautiful shells. They look like microscopic geometric snowflakes or tiny, spiky alien spaceships made of clear glass and chalk.
Beautiful and absolutely essential.
They are the foundational base of the entire ocean food chain. But more importantly, they are the secret to how those deep-sea monsters survive at the bottom. Because there is absolutely no sunlight at the bottom of the ocean, there are no plants or seaweed growing down there, so what does everyone at the bottom eat?
They wait for the food to come to them.
Well, when those billions of tiny glass plankton die at the sunlit surface, their shells and organic bodies slowly begin to sink down into the dark. If you shine a light down there, it looks like a never-ending slow-motion underwater blizzard.
Scientists literally call it marine snow.
It is a constant, steady shower of biological crumbs raining down from above, providing the vital food source that sustains all life in the abyss.
It is a beautifully balanced, interconnected system. Life at the sunlit surface, directly feeding life in the dark depths. However, the scientific journey of the Challenger wasn't exclusively a parade of brilliant discoveries.
Oh, there were some mess-ups.
It was also a rigorous process of correcting major, embarrassing errors made by the scientific establishment. This brings us to a fascinating investigation into the mud, the slime, and a highly publicized mistake involving a substance called the primordial slime.
This is a fantastic story because it shows why true science means being willing to admit when you are totally wrong. Years before the Challenger expedition even launched, a very famous, highly respected scientist was examining a sealed jar of old sea mud that had been dredged up from the ocean.
He felt something strange in it.
Inside this mud, he found a clear, gooey, mysterious jelly. He officially named it Bathybius heckelii, and he proudly announced to the entire world that he had discovered the primordial slime, the original ancient living goo at the bottom of the sea that all life on planet Earth originally evolved from.
It was a sensational, world-changing claim that captured the public's imagination. Everyone thought we had found the origin of life.
But aboard the Challenger, the expedition's lead chemist, John Young Buchanan, was specifically tasked with finding more of this miraculous, life-giving slime in its natural habitat. He meticulously tested sample after sample of fresh, freezing mud dredged directly from the deep ocean floor.
But he couldn't find the living slime anywhere. It was completely absent.
Then, observing the exact procedures used by his predecessors, he noticed a crucial, easily overlooked detail. The gooey slime only seemed to magically appear in the jars after the scientists added high-proof preserving alcohol to the mixture of seawater and mud.
Which they added to keep it from rotting during the long voyage home.
So Buchanan sets up a controlled experiment. He runs a bunch of tests right there on the gimbaled tables, mixing chemicals, and he realizes the famous, world-changing primordial slime wasn't alive at all. It was completely fake.
A simple chemical reaction.
When you pour strong alcohol into highly salty seawater, the two liquids react and create a gooey chemical precipitate, a physical substance that separates out of the liquid that just happens to look exactly like a living, clear jelly. The famous scientist hadn't found the origin of life. He had accidentally invented a chemical reaction in a jar and convinced himself it was alive.
To his immense credit, when Buchanan published his definitive chemical evidence from the Challenger, the original scientist who made the claim gracefully and publicly admitted his mistake.
That takes guts.
It does. It's a vital lesson for anyone interested in discovery. True science doesn't mean you're always right. It relies on rigorously testing your evidence, questioning your own assumptions, and having the intellectual integrity to look at the data and say, I was wrong.
Totally. It's how we learn. And while the magic slime turned out to be a bust, the real magic of the expedition was actually hidden in the actual mud itself.
Thanks to John Murray.
The energetic Canadian scientist was absolutely obsessed with the mud they brought up in the hollow tubes of the Bailey sounding machines. He would sit and stare through his clamped microscope for hours at a time, analyzing every single scoop.
And what did he find?
He realized that the deep ocean mud wasn't just plain dirt washed off the continents. It was actually made of billions of crushed up, dead plankton shells. He called these massive, thick layers of shell mud oozes.
But as the soundings reached the deepest, most extreme parts of the ocean, beyond a certain depth, the immense pressure and cold chemistry of the water actually dissolved those fragile calcium shells before they could even hit the bottom.
So no oozes down there.
In these absolute deepest, quietest zones, Murray found a very fine, completely different type of sediment known as red clay. And within this deep red clay, he made a discovery that sounds like it belongs in a science fiction novel.
He took a strong magnet and ran it through a sample of the deep red clay. When he pulled the magnet out, it had picked up these incredibly tiny, perfectly round metal spheres. He analyzed their composition and realized they were cosmic spherules.
Space dust.
They were microscopic meteorites and literal stardust. These were tiny pieces of asteroids from outer space that had burned through Earth's atmosphere, fallen into the vast ocean, and slowly sunk miles down to the deepest, quietest parts of the seafloor, where they sat completely undisturbed for centuries.
The Challenger crew literally reached into the dark abyss and pulled up dust from outer space.
It is a poetic realization that our planet is intimately connected to the broader cosmos, even in its darkest depths. Now, to truly understand how all these different physical layers of the ocean interact, the fresh rainwater at the surface, the salty water, the deep, freezing, heavy water at the bottom, we don't have to rely solely on Victorian records.
No, we can actually observe these physical principles in action today.
Yes. You listening right now can actually recreate the physics of the deep ocean right in your own kitchen with an awesome activity we call the ocean density jar.
A great little experiment.
All you need is a tall, clear glass jar and a few common liquids. First, you take some heavy, thick corn syrup, dye it dark black with food coloring, and pour it into the bottom of the jar. That thick layer represents the super heavy, high-pressure, freezing water sitting at the very bottom of the deep trench.
Then the next layer.
Then you take some blue dish soap and slowly pour it over the back of a spoon so it gently sits right on top of the black syrup. That layer is the dark abyss. Next, you mix some blue food coloring into regular tap water and pour that carefully on top.
We're getting lighter now.
Then add a layer of yellow vegetable oil to represent the twilight zone where the light starts to fade. And finally, pour a layer of rubbing alcohol on the very top to represent the lighter surface water.
If you pour them carefully and slowly, the distinct liquids will perfectly stack on top of each other without mixing together into a muddy mess.
Because of the density.
This happens because each liquid has a different physical density, meaning some are fundamentally heavier and more tightly packed than others. This fun experiment is an exact miniature model of how the real global ocean operates.
Cold, incredibly salty water near the poles is very dense and heavy, so it sinks all the way down to the bottom of the ocean, while warmer, fresher water stays near the surface.
This massive, continuous sinking of heavy, salty water at the freezing poles actually acts like a giant, invisible engine, driving massive, powerful, global ocean currents all around the world, distributing heat and nutrients.
It's so cool to see the complex physics of the entire planet working right there in a glass jar. Okay, so let's bring the ship home. The Challenger crew spends 4 grueling, exhausting years doing all of this. They sail 68,000 miles across the globe.
They survive violent storms.
They dodge massive Antarctic icebergs. They discover space dust, faceless fish, and hidden underwater mountains. Finally, in May 1876, the weary, weather-beaten wooden ship sails back into port in England. The physical journey across the waves is over.
But here is where it gets incredibly fascinating. The true scientific journey was just beginning.
Because they brought so much back with them.
The expedition had accumulated a literal mountain of raw data. They had hundreds of thousands of preserved biological specimens floating in jars, heavy crates filled with deep-sea mud, and countless logbooks packed with precise temperature readings and depth charts.
Too much for one team.
It was vastly too much information for any one person, or even the small crew of scientifics, to process in a lifetime. So the specimens were meticulously packaged up and shipped out to 75 of those brilliant, specialized scientists around the world.
And it took them quite a while to go through it.
It took 20 solid years of relentless, coordinated work to analyze every shell, identify every fish, check every temperature calculation, and finally publish the findings.
20 years of homework. When they finally finished cataloging everything, the official Challenger reports took up 50 massive, heavy volumes and contained an unbelievable 29,500 pages of pure science.
The publication of these reports is officially considered the defining moment when the modern science of oceanography was born.
Before the Challenger expedition, science was heavily segregated into separate silos. Geologists strictly studied rocks, biologists strictly studied animals, and physicists strictly studied water currents.
But the sheer volume and interconnectedness of the Challenger reports proved unequivocally that you cannot understand the ocean by looking at just one isolated piece.
The biology of the plankton, the chemistry of the dissolving shells, and the geology of the ocean floor are all inextricably linked into one massive, beautifully complicated, interconnected system.
And obviously, the technology we use to study that system has changed a lot since the 1870s.
We don't use 181 miles of heavy hemp ropes and coal-fired steam engines anymore. Today, modern scientists map the ocean floor using incredibly fast, multi-beam sonar, which bounces sound waves off the bottom of the ocean to instantly paint a highly detailed 3D picture of the underwater mountains.
Instead of blindly dropping a heavy iron net into the dark and hoping they catch something, modern explorers use ROVs.
Remotely operated vehicles. These are high-tech, glowing robotic submarines equipped with precise robotic arms and crystal-clear HD video cameras that can gently, carefully pick up a single glowing jellyfish without hurting it.
And instead of lowering thick glass thermometers on strings, we have deployed a network of thousands of robotic Argo floats that continuously dive down, record the temperature, and beam the data directly to satellites in space.
The technological advancement is truly breathtaking. It allows for precision the Challenger crew could only dream of. But this raises a critically important question. With all our modern satellites, advanced robotics, and instant global communication, why should we care about a dusty stack of data collected by Victorian scientists using hemp ropes and glass tubes 150 years ago?
Why does the Challenger expedition still matter to us today?
That is the ultimate question. What does this all mean for us right now, living in the modern world?
The answer lies in the most pressing issue of our time: Climate change.
Mhm.
Without ever intending to, the meticulous scientists aboard the Challenger created a pristine, irreplaceable historical time capsule.
Because they recorded everything so perfectly.
Their exhaustive data provides us with a comprehensive, highly accurate snapshot of the global ocean exactly as it was before the widespread burning of fossil fuels significantly altered our planet's atmosphere. Today, modern climate scientists take the exact, verified temperature readings recorded by the Miller-Casella thermometers in the 1870s and compare them directly to the vast amount of readings from our modern robotic Argo floats.
And the results of that comparison are absolutely stunning. Because the Challenger crew was so incredibly careful and precise with their Victorian instruments, modern scientists were able to prove definitively that the global ocean surface has warmed by 0.59 degrees Celsius over the last 150 years.
That might sound like a small number, but for the entire global ocean, it represents a massive, dangerous amount of absorbed heat.
And the historical impact extends deeply into the biology as well. Recall those microscopic plankton we discussed, the foraminifera with their beautiful, intricate calcium shells that rain down as marine snow.
Scientists working at the Natural History Museum in London took the 150-year-old plankton shells, perfectly preserved from the Challenger expedition, and placed them under modern microscopes. They then compared them directly to the exact same species of plankton shells living in the ocean today.
And they found a big difference,
They discovered that the modern shells are significantly thinner and more fragile.
which provides direct, undeniable physical proof of ocean acidification. Because human activities are pumping massive amounts of carbon dioxide into the air, the ocean acts like a giant sponge and absorbs it. This changes the chemistry of the water, making the ocean slightly more acidic.
But that acidic water makes it harder for the tiny plankton to build their shells, causing them to dissolve faster.
So, by simply being incredibly curious, braving the storms, and meticulously writing every single detail down, these Victorian explorers working on a creaky wooden boat accidentally provided the exact baseline data we need to understand and protect the future of our entire planet today.
It is a profound, enduring legacy. The voyage of the HMS Challenger proved that when humans combine their courage, their engineering ingenuity, and a relentless desire to ask big questions, we can fundamentally change how we understand the complex world around us.
Okay, let's take a deep breath and recap this absolutely epic 4-year exploration. We started with a world that firmly believed the deep ocean was a dark, dead, flat desert filled with imaginary monsters.
And we completely reshaped that view.
They took a rugged, wooden Royal Navy warship, stripped out its heavy cannons, and completely transformed it into a brilliant, floating science lab. Using nothing but miles of thick rope, heavy iron weights, and the muscle of a steam engine, a mixed crew of tough sailors and brilliant scientists shined a light into the pitch-black abyss.
They mapped the longest continuous mountain range on Earth, found the absolute deepest trench on the planet, and proved once and for all that the ocean is a vibrant, moving, living system filled with glowing, bizarre, and incredibly beautiful creatures.
It stands as a brilliant testament to human endurance and the unyielding power of scientific curiosity. And we want to express our most sincere, profound gratitude to you for joining us on this incredible historical exploration. Looking back at the courage of the past helps us better navigate the challenges of our future.
Thank you so much for hanging out with us and exploring the amazing story of the HMS Challenger. But before we let you go, we want to leave you with one final, absolutely mind-blowing fact to chew on.
Oh, this is a good one.
Despite all the incredible groundbreaking work of the Challenger expedition, and despite all our modern sonar, deep-sea robots, and orbiting satellites, more than 80% of our global ocean is still completely unmapped, unobserved, and unexplored by human eyes.
We actually possess better, higher-resolution maps of the dry surface of the planet Mars than we do of the bottom of our own ocean.
Marine biologists estimate that there are still up to 2 million undiscovered species living down there, waiting quietly in the dark to be found. The great question is, who will be the brave explorer to find them? It could very well be you.
How absolutely amazing is that? 2 million undiscovered wonders and glowing marvels just waiting in the dark for someone brave enough to look for them. Until next time, keep your curiosity anchored and your sails full of wonder stay salty, explorers, and we'll catch you on the next tide here on Saltwater Stories.